let's look at conservation of momentum in 2 dimensions, okay? So here is the first question. We'll look at, and we'll use the example of curling because that's going to be our focus, all right? We'll look at a curling stone striking another curling stone, and then we're going to figure out the final velocity of the second stone, okay? Oh, I got to plug in my little tablet, which I didn't do. 1 second, I'll just plug this in. Okay. Go. All right. So let's take a look at this question. Okay, so we have a curling stone going east. So let's say this is my curling stone. Okay, it's going east, and then it strikes another stone. Okay, and then so here's my second stone. It's over here. Okay, then after the collision, this we'll call this stone 1. This is stone 2. So after they collide, so here's stone 1 now. Okay, and then stone 1 goes this way. Okay, southeast. So we know that this is 45 degrees. We want to know what's the velocity of the second stone. Okay, so we're going to try to figure out. Now, why didn't I give you mass here? Because we know that for momentum, P equals mv, but you just saw in the video that the curling stones all have what? Same mass. So the mass is going to cancel out. So we can just say the initial velocity is going to equal the final velocity, right? Okay. So because there's 2 dimensions, we have to conserve the momentum in both dimensions. So what we'll do is we'll start with looking at the x component. Okay? So if you look at this curling stone, it's traveling at 1.4 meters, sorry, 2 meters per second, not 1.4. It's traveling at 2 meters per second east. Okay? Now, we know that one of the stones travels 1.4 meters per second southeast. So we can go ahead and extrapolate and figure out what that x component is. What would that be? So it would be this component right here, and that would be cosine 45 times 1.4. This is 1.4. So that must be what? About close to 1. 0. No, it can't be. 0.99. No. The second, so the stone, here's stone 1, right? It's traveling at initially 2 meters per second. Then there's a collision here. We don't know which way stone 2 is going, but we know stone 1 is going to be going 1.4 meters per second southeast. This angle is 45. So this is, yeah, it's close to 1. We'll just say 0.99. Okay. Meters per second east. And then we're left with the final of the second stone. Well, we know what that must be now, right? It has to be 2.0 meters per second east minus 0.99 meters per second east. So that must be, if you round it up to 1, we'll just round it up to 1. We'll just say it's 1 meter per second east. Then the y must also be conserved. Okay, so that y component must also be conserved. Oh, here's the thing. What's the y component for the initial stone? It's 0. That's not going north or south. We have north and south, by the way, as our north-south. It will be our y component, and then east-west will be our x component. So initially, the momentum along the y is 0. And that has to add up then to this component plus the other one. Well, in this case, it's going to be, well, let me put plus for now, okay? Okay, so, what is this? So V1 prime, okay, here's V1. This is also going to be, we'll just say it's 1, right? So if this is 1, then V2 would have to equal to negative V1 prime, which means if V1 prime is 1, that means V2 is equal to negative 1 meter per second. Okay? Now, what do you think the negative means here? Well, we're talking about north and south. I did not define one direction. I said one direction. You guys okay with that? I mean, girls get excited when. Okay. So we use V1 prime as 1. The negative 1 must be what? The opposite direction. So this one is pointing south. So the negative 1 must be the other way. So V2 must be 1 meter per second south. Now, this makes sense because the second curling stone then would be traveling 1 meter per second east, 1 meter per second north. So then we already know what this is going to be. This should also be then 1.4. Because this triangle is exactly the same as this one. It happens to be in this case because the angle is what? 45 degrees. The next one, it won't be. Okay? The next one, it won't be. But you see the big idea, right? The big idea is you got to conserve the momentum, but you got to conserve it in all directions. Okay? So let's look at we'll look at one more question. In this case, the question is going to be a little bit more challenging because we're missing some information. Okay? Alright, so let's look at the last question. So we're going to use curling stones again as an example. We have the same initial velocity. So here's my curling stone. Call it 1. It's traveling at 2 meters per second east. It's going this way. It collides with the second stone. Okay? But we don't know what the speed is after the collision. But this is what we do know. We do know that the first stone travels east 30 degrees south. So it goes like this. Okay? So this angle is 30 degrees. But we don't know what the speed is. And the other one goes east, but 20 degrees north. Okay? So because the angles aren't the same, then in this case the velocities won't be the same. Alright? Okay, but here's what we know. We know that if we add it up, so if we look at this vector here, and we thought about it in terms of a y and an x, and here's my x, and here's my y, we know that the x components have to add up to what? Yeah, very good. So this is what we know. We know that for the x component, we know that they have to add up to 2. So we know that, call this V2 prime, and we'll call this V1 prime. So we know that V2 prime for its x component and V1 prime for its x component have to add up to 2. Right? So we know. We also know that the y component has to add up to what? 0. So that means the v2 component along the y and the the v1 component along the y have to add up to 0. Okay? So far so good? Okay. So let's expand this a little bit more. Let's take a look at the y first, okay? In this case, it actually doesn't really matter, but let's look at the y. So here's what we know about the y. We know that the v1 prime y component has to equal the negative of the v2 prime y component. Agree with that? Now, what would this v1 prime though be? So here's my triangle. It would have to be what? It would have to be v1 prime times sine 30. My v2 would have to be v2 prime times sine 20. Okay? So we can go ahead and we can actually isolate for v1 prime. We could say v1 prime would equal to v2 prime sine 20 over sine 30. Now, if you want to actually put in sine 20 and sine 30, we could say v1 prime is equal to what then? What's sine 20 over sine 30? So we can say that v1 prime is equal to negative 0.68, you said? 68 v2 prime. Okay? So far so good? Now we can go back to our Vx equation. So let's go, if we go back to our Vx equation, we could say, alright, well, let's change the direction. So in our Vx equation, 2 is equal to this was our original equation, right? We know that that has to add up to what? 2. Okay. So this we can plug in now, right? Because we have basically, we know what v1 prime is. So we can say that 2 is equal to v2 prime. Now the x component, what would that be? Wouldn't be sine theta, it would be what? Yep. So it would be cosine. v2 prime was 20 degrees. And we know what v1 prime is. We know it's negative 0.68 v2 prime. But again, we need the x component, so we got to multiply that by cosine. Because if we look at v1 prime, it's 30 degrees times cosine 30. By the way, where have you seen this before? This idea of setting one thing equal to another and then substituting it into the next equation. This is the exact same thing we did with statics. Remember an object's being held by 2 cables? Right? It's the exact same method. Exactly the same. Okay, so let's take a look at this. So what is, let's expand this. So 2, so what's cosine 20? So 0.94 v2 prime. And then what's cosine 30 times negative 0.68? 0.59 V2 prime. Now we can isolate for V2 prime. We can say that 2 is equal to 0.35 V2 prime. And now we can go ahead and solve for V2 prime. That would be 2 over 0.35. What is it? 5.71? So 5.71. 5.71? 5.76. What's V1 then? Oops. So what V1 prime is negative. What is it? Negative. Okay. So we got 5.76 and 3.94. Okay. That's really odd. Did we do something wrong? Oh, yes. We made a mistake with the sign. Yeah. Okay. That's okay. That's alright. We can easily fix this. We made a mistake with the sign because here we know, okay, in the previous example we didn't know the direction of the curling stone, but here it's being laid out that it's actually going to be the opposite. So you see how we have it set up as V2 plus VI? It actually should be V2 minus VI. Sorry. It should be minus VI. Because these numbers aren't making sense. 5.76 and 3.94. Okay, so let's go ahead and fix this. I apologize for that. So this would be then plus, right? This will be plus, and that will be plus, right? Okay. So that would mean this is plus. It's a quick fix. This is plus. So this now becomes what? 0.94 plus 0.59? 1 point. V2 prime. Now we can go ahead and solve for V2 prime. Now that makes more sense. 1.3. And then we define V1 prime as plus 0.68. Okay. So what would that be? 0.89. Okay. Now, in the previous answer we got, the momentum would have been conserved, but it would have predicted that one of the balls would actually be traveling in the opposite direction. We'd be going something like this. But because the diagram is clearly laid out that they're going both east, then the numbers that we got didn't make any sense at all. Okay? Because there's no way that the stone could be traveling faster than the initial speed. Right? Your curling stone was traveling at 2 meters per second, the other one was stationary. How could one of them end up traveling at 5? Or was the other answer 3 point something? So if you get a nonsensical answer like that, the method was fine. It was just, see how that one little sign changed everything? Okay? So, if you get, use your common sense. If it doesn't look right, just go back and make sure that it's most likely going to be a sign that's not right. So, let's see if these numbers make sense. 1.3, so we're predicting V2 to be 1.3. So this is 1.3, and the other one is basically, I'm going to round it off to 0.9 meters per second. Okay, and then you can always go ahead and double check to see if this, because remember, what does the x component have to add up to? So if you take 1.3 cosine 20 and 0.9 cosine 30, what should it add up to? 2. So let's double check that. So what's 1.3 cosine 20 plus 0.9 cosine 30? It should add to at least close to 2. Okay. Alright, so there you go. It works. Okay, ladies? I'm going to write down it works. Okay, that's it. The end.